welcome to This Explainer. Today, we're diving into a genuinely thrilling scientific mystery that kicked off right at the dawn of the 20th century. I mean, picture the scene. It's the year 1900. Classical physics, built on the absolutely brilliant foundations of giants like Newton and Maxwell, well, they thought they practically had everything figured out. The universe made total sense. But that confidence? It was about to be completely shattered, making way for the incredibly strange and fascinating world of quantum mechanics. You know, the exact same science that powers your smartphone and all modern computers today. And this famous quote right here really captures that exact moment perfectly. Lord Kelvin, an absolute titan of classical physics, stood before the Royal Institution and delivered a lecture optimistically pointing out just two tiny clouds, or unresolved anomalies, hanging over the otherwise perfectly clear, sunlit skies of classical science. He totally assumed these were just minor details, right? Just little things to be ironed out. But oh man, he couldn't have been more wrong. Those two little clouds were actually the leading edge of a massive reality-bending storm.
Section 1. Cloud 1. The atom's secret structure.
So this first cloud actually started as a really puzzling optical mystery in a Dutch laboratory. Now, decades earlier, the great Michael Faraday had tried this exact same experiment, putting a glowing sodium flame in a magnetic field just to see if the light changed, but he found absolutely nothing. His equipment just wasn't sharp enough. But then, fast forward to August 1896, and Peter Zeeman gives it another shot. Using a super powerful electromagnet and instrument sharp enough to basically act like a super prism, Zeeman looked closely at the emitted sodium light and noticed something bizarre. The sharp, distinct spectral lines of the light didn't just sit there. No, they actually spread out into wider bands the second the magnetic field was turned on. Obviously, Zeeman took this bizarre result straight to his mentor, the brilliant theoretical physicist Hendrik Lorentz. And Lorentz? Well, he immediately applied the standard rules of classical physics. He confidently predicted that inside the atom, there simply must be oscillating charged particles emitting this light. When you apply a magnetic field, that magnetic force actually curves those straight vibrations into circular motions. So, based on this incredibly elegant classical model, Lorentz predicted the light should split into exactly three distinct components: a central line and two shifted lines, each with a very specific polarization. And guess what? Initially, Zeeman's better instrument seemed to confirm exactly this triplet. It looked like a massive win for classical physics. But what's truly staggering here is the math that came out of that experiment. Just from the size of the light's frequency shift, Lorentz was able to calculate the charge-to-mass ratio of whatever it was that was vibrating inside that atom. And the result? The ratio was a staggering 1,000 times larger than that of a hydrogen ion. Let that sink in. This meant whatever was oscillating inside the atom was incredibly light, and it carried a charge. Without even fully realizing it, classical physics was peering right at the discovery of the electron before J.J. Thomson even officially announced it. But, as you might guess, the classical celebration didn't last long at all. Over in Dublin, an experimentalist named Thomas Preston started testing this supposed perfect triplet rule on other elements, like cadmium and zinc, and what he found completely broke Lorentz's simple model. Instead of a neat little triplet, Preston found lines that split into chaotic, complex patterns of 4, 5, or even 6 components. This wild mess became known as the anomalous Zeeman effect. The inescapable, honestly terrifying conclusion for classical physicists was that a single oscillating charge simply could not explain this. The atom clearly had a deep, complex, hidden internal structure that classical physics was entirely blind to.
Section 2. Cloud 2. The black body radiation problem.
So while the atom's internal structure was causing major headaches, Kelvin's second cloud was quickly gathering on the horizon. The challenge here was a problem that had literally stumped scientists for decades. I want you to think of a perfectly absorbing cavity, an idealized oven, basically, known as a black body. It emits thermal radiation that depends solely on its temperature and the frequency of the light, entirely independent of what the cavity itself is actually made of. The ultimate goal? To mathematically derive exactly how much energy a hot cavity radiates at each wavelength, purely from foundational physical principles. It was essentially the holy grail of thermal physics. To put the leading classical theories to the test, an experimentalist named Heinrich Rubens developed a brilliantly clever step-by-step technique called residual rays, or Reststrahan. He produced radiation from a heated cavity, and then repeatedly bounced that light beam off surfaces made of materials like fluorite and rock salt. Each reflection acted like a sort of filter, stripping away unwanted light and purifying the beam, over and over, until he had isolated pure, incredibly narrow bands deep within the far infrared spectrum. And this experimental breakthrough, it blew everything completely wide open.
Using these pure infrared rays, Rubens proved that at these super long wavelengths, the radiation intensity just kept growing linearly as the absolute temperature increased. Now, the widely accepted classical formula of the day, Wien's law, well, it predicted that the intensity should eventually hit a ceiling and just saturate. But nope. In the deep infrared, Wien's law was completely and utterly broken.
Section 3. The ultraviolet catastrophe. Desperate to explain Rubens' new data, theorists fell back on trying a purely classical approach. In June of 1900, Lord Rayleigh tackled it by calculating the standing electromagnetic waves inside the cavity. It's kind of like counting all the different ways a guitar string can vibrate inside a wooden box. He applied a classical rule called the equipartition theorem, which basically insists on giving an absolutely equal share of thermal energy to every single wave mode. But here's the catch. Because higher frequencies have shorter wavelengths, you can technically fit an infinite number of those standing patterns into the cavity. And because of that infinite number of patterns, the math went completely off the rails. It led to what physicist Paul Ehrenfest later dramatically dubbed the ultraviolet catastrophe. Think about it. If every single one of those infinite high-frequency modes gets an equal share of heat, classical physics is suddenly predicting a literal physical impossibility. It predicts that an oven in thermal equilibrium would radiate infinite energy, just instantly vaporizing everything around it, including, unfortunately, the physicists trying to use it to make a cup of tea. So, physicists had effectively hit a massive brick wall. On one side of the equation, you had Wien's law, which worked perfectly at short wavelengths but failed miserably at long ones. On the exact opposite side, the new Rayleigh-Jeans calculation worked perfectly at long wavelengths but diverged into an impossible infinity at short wavelengths. It was a total mess, and classical physics was entirely incapable of unifying them. This left the entire scientific community staring at a profound, honestly terrifying crisis. I mean, how exactly do you fix a classical formula and, by extension, an entire scientific worldview that confidently and mathematically guarantees an impossible infinite result? Section 4. Planck's quantum leak. Just look at how rapidly the classical foundation crumbled. It's wild. In just 4 years, from Siemens' line splitting in 1896 to Kelvin's speech to Rayleigh's infinite energy calculation in the summer of 1900. Fast forward to October of 1900, and the brilliant physicist Max Planck receives Rubens's infrared data. Realizing classical physics was completely broken, Planck hastily hacked the mathematics, essentially creating an interpolation formula, a math trick, really, just to bridge the two broken laws together. Now, it fit the data perfectly, but the problem? It had zero physical justification. So Planck spent the next few weeks desperately trying to find a physical reason for why his math trick actually worked. And on December 14, 1900, he presented his revolutionary derivation. To avoid that impossible infinite energy, Planck had to take a radical, totally desperate step. He proposed that energy wasn't a continuous, flowing stream like everyone thought. Instead, it could only be exchanged in discrete, finite portions, little packets, or quanta, and the size of those packets was strictly proportional to their frequency. Literally just like that, our entire understanding of matter and energy was totally revised. Lord Kelvin's two tiny little clouds had unleashed a massive, universe-altering storm. The big takeaway here? The anomalous Zeeman effect proved the atom actually had a hidden, incredibly complex internal structure. And the blackbody problem? It proved that the fundamental nature of energy wasn't a smooth, continuous wave at all. It was jagged, it was discrete, it was quantum. Which leaves us with a truly fascinating question to ponder as we wrap up this explainer. When Planck introduced those discrete packets of energy back on December 14th, historians still debate his true intentions. Like, did he believe it was just a temporary mathematical band-aid? Or did Planck actually realize his desperate fix had just permanently destroyed classical physics and birthed the modern quantum universe? It's a stunning reminder of how chasing even the smallest anomalies can completely rewrite reality. Thanks for exploring the gathering storm with me today.